This project will focus on proposing a solution to volumetric denial of service detection using k-means clustering and the naive Bayes classification model. So why is this important? Why is this problem domain important? Well, we can see that over the last few years, the scale of these attacks have grown tremendously. In 2020, NetScout reported over 10 million DDoS attacks over the course of the year. That had grown massively from 2019 and 2018 as well. And that's over 800,000 attacks per month. And this is supported by, Cisco's report that they expect these types of attacks to grow by 14% to around 15 million by 2023. So the recent Gartner CFO survey discovered that 74% of companies plan to shift some of their workforce into remote positions, while 4% of companies plan to shift over half of their workforce into remote positions post-COVID. These companies include Microsoft, Amazon, Facebook, American Express. This will mean that online dependencies on services and assets will increase alongside the growth in DDoS attacks, making them more impactful, more harmful to online businesses across the world. So this chart shows the different attack vectors that denial of service attacks can take. As you can see, SYN Flood makes up a huge portion of what is affecting the industry today, with 92%. So our solution will focus on tackling this specific issue, which is a volumetric denial of service attack. Some of the common limitations of the detection models that we've reviewed in this dissertation is things like false positive rate, computational complexity, and asymmetric attacks. So for the false positive rate, a lot of the detection models aren't very optimized in terms of only detecting what is actually an attack. A lot of them throw in legitimate traffic as well, and that can impact on legitimate users and deny them of the service that we're actually trying to assure. Computational complexity just completely deems some approaches unfit for use in practical industry scenarios. So we're looking to create something that's actually practical to implement. And asymmetric attacks, some detection models that we review can't detect asymmetric attacks because of their low bandwidth nature. Things like behavioral anomaly detection can, but traffic anomaly detection can't. So in the next section, I'll be talking you through the proposed solution that we're going to take to combat these limitations that we've just discussed. So I'm just going to run you through some of our data pre-processing before we started our unsupervised phase. So we read in the CSV file, which is a dataset comprised of legitimate traffic and TCP SYN Flood attack. Now, because of the constraints of this project, specifically hardware constraints, we couldn't actually process all of this data. So we've selected one of the attack windows to process, and we're filtering out everything else that's not inside that attack window. The specific attack window has around 10% packet ratio between legitimate and malicious packets. Then we're going to convert all of the values that we reasonably can to numerical. So that is the SYN and ACK values of not set and set to 0 and 1. And then we're just going to remove all of the not a number or NaN values from our dataset because they can't be processed by our k-means clustering. And once this is done, we're going to output it into a new formatted CSV file. So over in the unsupervised phase, we're going to initiate a Spark context which connects to the Spark framework that we've set up prior to this. We're going to read in the CSV file to our PySpark data frame, and we're going to index the destination IP, source IP, and time till live columns from strings to numerical, so again we can process them. And then we're going to drop all of the columns that we deemed irrelevant for this process. Now we have tested this with different parameters and different columns, or different features should I say. The ones we're using in this example is frame length, destination port, SYN and ACK, the destination IP index, and the time till live index as well. So from here we're going to vectorize them into a features column, and then we're going to go ahead and standardize our features, and this just makes sure that k-means has equal value, or it weights them all the same when it's processing them, so it doesn't treat the frame length any different to the ACK flag, for example, even though one has a value of 1500 and then the other only has a value of 1. They'll all be treated equally and of equal importance when it's clustering. So we're going to go ahead and drop all the columns that we don't need, apart from the standardized data. And then we're going to put that into a 2D object or a list. From there, we're going to read that list into our principal component analysis, which just compresses the amount of components that we actually need to efficiently cluster without losing data variance. So here we're just outputting a graph to visualize how much data variance we still have for each principal component. So you can see at one principal component we have around 40% variance, which isn't very good. And then at 5 principal components we have around 98% variance, which is more optimal. So here we select 5 principal components just to save speed, but we've tested this with principal components between 1 and 6, and we're going to fit our standardized list which we made earlier to our PCA. From here we will predict the optimal number of clusters that we need for this process. So we're just going to run a for loop testing the Euclidean distance for each value of k from our principal components that we made earlier, and then here we're using the elbow method to determine how many clusters we should actually use for this data set. Here we identify that we need 6 clusters, so that's what we select, with a random state of 42, just so it's reproducible after this process is finished. And then we append all of our clustering labels that we've just made to our principal components in this list here. Once we've done that, we read in the data that we dropped earlier, we read in the CSV file, we join our labeled data and our data set together. So now all of the data rows, they've got labels, and then we output it and we save that as another CSV. Now once we read that in, we can drop the PCA columns that we made, and we can start extracting some metrics about the data. So we can see how many data points are in each cluster, and we can see how many attack data points have been clustered together, and we can start extracting things like false positive rates, accuracy, true negative rates, and then this kind of leads into how we tested it. So moving on to our classification phase using naive Bayes. So again, we initiate a Spark context and read in the now labeled data from our unsupervised phase, and we drop all of the PCA values because we no longer need those. Again, we're just indexing the strings like IP addresses that we can't process otherwise, and then we're extracting features as a vectorized column. Now we're just going to drop all of the columns that we no longer need, so we're left with the label and the features, and then we're going to split the data set into a training set and a testing set, and the split for that will be 70% and 30%. So here we initiate our naive Bayes classifier. We set the smoothing parameter to 1, just so if our data set isn't comprehensive, or there are some outliers or values which aren't represented properly, it won't assign a 0 probability to something, so there'll always be a baseline probability even if the data set isn't complete. This is actually especially important because we can't process such a large amount of data just because of the constraints of this project. So this was a very important decision that we made here. So here we're just extracting some metrics about the performance of our classification. We're filtering for the IP address where we know the attack is happening, and we're seeing what predictions are made based on what label it will be assigned to, so what it will be classified as. All the attack traffic is identified in this case. However, there is some legitimate traffic which is thrown in as attack traffic as well, which is less than optimal. So 12,828 attack packets are identified, which is 100% of the attack packets, and then 18,603 packets in total were predicted to be of that label. So we've got around about 5,000 legitimate packets which were predicted incorrectly. So those are the false positives that will be used to produce some of our evaluation metrics when we evaluate this project. The results and measurements of this implementation will be discussed in the submission evaluation and results section.